Hello all, I'm Siddharth Kaur and I welcome you. This is the part 2 of Introduction to Matlab IDE and I will be continuing from example of script. The following is a simple example of a script file that shows the preferred program style that is used in Matlab. Here the speed of falling object dropped with no initial velocity is given as a function of time t by v is equal to gt, where g is the acceleration due to gravity. In SI units, g has a value of around 9.81 meter per second square. Here we want to compute and plot t versus v, where t is between 0 to t final, where t final is the final time entered by the user. The script file is what is shown here in the slide. So we have defined g as 9.81, that is acceleration in SI units. Then we have an input for t final that we ask user to enter the final time in seconds. Then we define an arbitrary increment dt. Here in this case it is t final that by 500, that is point something phi, close to phi. Then we create an array of time from 0 to t final with increments of dt, and at the end we calculate the velocity v as g into t. Now we plot t and v. We label time axis as seconds and speed axis as meter per second. Now let us see what is the output for this. As v into gt is a linear relationship, this is what you will see in the plot. It will be a straight line with between at 45 degrees between time axis and the speed axis. So the speed will start from 0 and the time at 0, and it will reach to 100 and time at 10. So this is like one of the basic ways we write some programs in Matlab. Let's talk about help in Matlab. Matlab's help system is one of the most important parts of Matlab IDE. The major reason for the same is that everything in Matlab is so well documented and is supported by multiple references and literature. To help navigate the help system of Matlab, 4 things are to be known: the function browser, the help browser, help function, and additional help, or we say other resources. Function browser can be activated either from the help menu, or we can activate it in the command window with fx icon. This is basically a quick access kind of thing that provides easy access to the functions we have selected. It basically in a small window prints the whole function documentation. The help browser is a GUI based tool that basically is a navigator and result and display window. The content lists down all the documentation installed or available for the product, and one can browse or search in the search toolbar to find out the correct function. Help function is a set of commands that can be used in the command line to access the information about Matlab functions. These include help function that is followed by the name of the function we want the information about. Then we have look for function that allows us to search a function on the basis of a keyword. Then we have doc function that displays the documentation for the Matlab functions. Typing doc followed by the toolbox name or function name displays the documentation for the specified toolbox function. Shown here is a list of commands that are available for help. We have function doc that displays the start page of the documentation in the help browser. Then we have function doc followed by the function name that displays the documentation for the specified Matlab function. Similar to this, we have doc function followed by the toolbox name that displays the documentation specific to the mentioned toolbox. Then we have help command that displays a list of all function directories with the description that what each category represents. Then we have help function followed by the function name that displays the description of the specified function. Then to see some topics inside the help window, we call the help win function followed by the topic name. Last we have look for command followed by the topic name that displays a brief description that includes specified to the provided keyword in the topic name. This course, that is basic of Matlab, has been designed keeping in mind the basic engineering problems. So in this slide, I will be talking about problem solving methodologies for such kind of problems. This will give you a fair idea like what should be the plan of action when you are solving problems with the basic engineering problem. These tips are basically a plan that can be used for any general kind of solution for any kind of engineering problem, be it mechanical, electrical, or something else. Now the first step is to understand the purpose of the problem, like what is the problem, what it is trying to solve. It's how you can simplify it, what in simple terms you can say about the problem, that kind of stuff. The second is collecting the known information. and it's better to collect all the related and known information. Some of it might we can use, or some of it might not be that much necessary, but it is recommended to have all the required information in one place. Third is we need to determine what information we need to find. There are some missing information might be there, or some dependent information might be there that we might need to calculate before we can proceed forward. So all these information we need to determine, like which we have to find. Then fourth is we have to simplify the problem only enough to obtain the required information. Here we can take any assumption just to get what we want. We should not go that deep into the problem, like say for example how high the ball has to bounce. So just we need to know the rebound height. We don't need to know how much force it has hit the ground or something like that. So we have to simplify the problem as much as possible. Then fifth is we need to draw a sketch and label any necessary variables that we might use. The sixth is we need to determine which fundamental principle will be applicable to solve our problem. Then seventh is we need to generally think about our proposed solution approach. We need to consider like other approaches before proceeding with our proposed solution. Why some solution might work, why some solution might not work. All these has to come into mind. All these have to come into picture. Then eighth thing is we need to label each and every step in the solution process. This is like the same thing we do by hand calculation, where we'll mark each and every step, so it is easier for us to trace back. Ninth is if we solve the problem with the program, we should hand check result. We need to hand check the results using a simple version of the program. Checking the dimension and units and printing the results of intermediate step in the calculation sequence can help us uncover some unknown mistakes or problems. Then finally, we need to perform a reality check on our answer. Like, does the answer make sense? We need to estimate the range of expected result and compare it with our own answer. We should not state the answer with extremely great precision than it is required. Say for example, we either require only integers, so we don't need to go into a like double float or something, as it is not at all required. So these are dependent on one of the following parameters, like precision of the information, simplifying assumptions, and requirement of the problem. We need to interpret the mathematics of the answers. If the mathematic produces multiple answers, we cannot discard them just like that. We need to know like what the answer means, what it stands for, or like it is telling something to us that we might have missed during our understanding of the problem. So these are all the points that we need to keep in mind while solving our problems using Matlab. Let's take an example that will clear how these problem solving things can be used. Let's take some random problem. Say a new packaging material can protect a package when dropped, provided that the package hits the ground at less than 25 feet per second. The package total weight is around 20 pounds and it is rectangular with dimensions of 12 by 12 by 8 inches. Like, we have to determine whether the packaging material provides enough protection when the package is carried by the delivery persons. Now let us solve this problem step by step. Step 1 is understanding the problem. The aim is to protect the package from falling from the hands of the delivery person and not from the moving truck. In practice, it is required that the person giving the instruction also is making the same assumption as the delivery person about this packaging assignment. So the first thing that is absolutely clear is we have to protect the package falling from the hands of the delivery person and not from anywhere else. Step 2 is collecting the known information. We know that these are the information that we know about the package. We know the package's weight, we know the package's dimension, and we know the maximum allowable impact speed for the package. So these are all the information that we know. We collect it and put it in one place. Step 3 is determining what information is to be found. This step involves in determining the information that are relevant and are need to be found. Although not explicitly mentioned, one of the key information here in this problem is determining the maximum height from which the package can be dropped without damage. So basically here we will be finding a relationship between the speed of the impact and the height at which the package is being dropped. Step 4 is simplifying the problem. This is probably the most difficult for some of the engineering problems. To perform this step, it is extremely essential that we are extremely thorough with the step 1. That is, we need to understand the problem completely. Here, in case of this falling package problem, I will make the following assumptions to simplify it far enough so that I can get my required information from it. The assumptions in this case are obvious and simple and might not be for other problems. The first assumption is the package is dropped from rest with no vertical or horizontal velocity. Second is the package does not tumble, as it might when dropped from a moving truck. The effect of air drag is negligible. The fourth point is the greatest height from which the delivery person could drop the package is 6 feet, and thus we ignore the existence of a delivery person that is 8 feet or 9 feet tall. Fifth point is the acceleration g due to the gravity will remain constant because the distance drop is only 6 feet and not much. So these are the assumptions that will help us simplify the problem. Step 5 is visualizing a problem and labeling any necessary variables. The best way to quickly know a solution to any problem is to visualize it. Here height h is shown and package is shown with mass m coming down with velocity v, and acceleration due to gravity is g. Step 6 is determining the fundamental principle that is applicable to solve the problem. As the problem involves a mass in motion, we can apply the Newton's laws of motion. Following are the relation that we know from Newton's law at the basic kinematics an object falling a short distance under the influence of gravity with assumption of no air drag or zero initial velocity. So basically we have a height versus time to impact, that is h is equal to half gt square. Then we have impact of speed versus time, speed v versus time t to the impact, that is v is equal to gt. And then we have conservation of mechanical energy law, that is mgh is equal to half mv square. Step 7 is considering the proposed solution. There are several ways in which we can propose a solution to this problem. What I am going with is law of conservation of mechanical energy. So we have mgh is equal to half mv square. This is the most efficient approach to solve for h. So using the conservation of mechanical energy, we get an equation for h as h is equal to half v square by g. This is an interesting thing. Notice that the mass m cancels out in the equation. So what does this mathematical thing signifies? This means that the mass of the package has no impact on the relation of impact speed and the dropped height. This is what I am talking about when we try to understand the mathematical part of a problem. This small equation tells us that the mass has basically no effect on how fast the object is falling and at what height the object is falling. Step 8 is labeling each step in the solution. Actually, because of the simplicity of this problem, there are not many steps that need to be labeled. We have basic principle, that is the conservation of mechanical energy, where we get the formula for h, that is half v square by g. Then we have the value of g as 32.2 feet per second square. Third is we are using these two information and we perform our calculation where we get the height as 9.7 feet. The code for same is written below. So we define variable g with speed of 32.2, then we define variable v with value 25, and then we write our equation h, that is v square by 2g. So we get an h that is approximately 9.7 feet. Step 9 is checking the dimension. Dimension check is something like shown in this slide. So we have to check whether the dimension meets our expected output dimension or not. So here we have to have the height in terms of feet. So now from half v square by g, we are supposed to get feet as a unit. So we have the velocity square as feet per second whole square, and then we have acceleration due to gravity unit, that whose unit is like feet per second square. After simplification, we get like something like feet square into second square by second square into feet. So the second square and second square gets cancelled out and we are only left with our final unit as feet. Hence the dimension, expected dimension, that is the feet, match with our calculated dimension, that is also the feet. Hence this is how we check the dimensions in our solved problem. Step 10 is to perform a reality check. Reality check is something that if we get a height in negative, we would obviously know something is wrong. Also, if we get a very large value, it also means that something is wrong in the calculation. However, the computed height in our case is 9.7 feet, so that does not seem unreasonable. Hence, we can say it has passed our reality check and the values are pretty much reasonable. This concludes our 10-step solution for our problem. This is how we approach a problem, approach any kind of general engineering or electrical or mechanical problem. Steps for obtaining a computer solution. Now, as we know how to tackle problems, we will see what are the steps we can take to obtain a computer solution to similar problems. Here are the 8 steps that are usually followed. We consciously, concisely and precisely state the problem. Focus is only on the problem at hand, small segments at a time. Then we specify the inputs for our program. Then we specify the outputs for our program. We work through the solution step by step by hand or by calculator, and we use the simple data if necessary. Then we write and run our program. The output that we get from our program is then compared with the hand solution. The output also goes through reality check, like does it make sense, like the estimate is within the range, or it is an expected result or it is not an expected result, and we compare it with our answer. Then we have an option to check the program for a range of reasonable values and perform a reality check on the results. Let us take an example and understand step by step how to get a computer solution. There is an image of piston, a connecting rod, and a crank for an internal combustion engine that is shown here. So when the combustion occurs, it pushes the piston down. This motion causes the connecting rod to turn the crank, which causes the crankshaft to rotate. Now our computing aim is to develop a Matlab program that will plot the distance d traveled by a piston as a function of angle A for a given values of length L1 and L2. L1 is the length of connecting rod and L2 is the length of crank. The importance of this plot is that it will help the designer of the engine to help select appropriate lengths for connecting rod, that is L1, and the crank, that is L2. So let's see what we know in this problem. We are aware about the typical values of these lengths, that is the length of connecting rod and the length of crank, that is 1 feet and 0.5 feet respectively. Also, as the motion is symmetrical about A, that is at angle A equal to 0, we need to consider angles within the range of 0 to 180 degrees. An equivalent trigonometric figure is also given. We can use the expression d is equal to L1 cos B plus L2 cos A. Thus, to compute distance d traveled by the piston at given length of L1 and L2 and angle A, we have to first determine the angle B. Now, equation in the last line shows the steps to solve for angle B. We have signs as sin A, we have the ratios as sin A by L1 and sin B by L2. From that, we can solve for B as a sine inverse of L2 times sin A whole divided by L1. From this, we will get angle B, and from there on, we can solve for the distance traveled by the piston. Now let us start with our solution. The step 1 is stating the problem concisely. So using these two equations, that is sin A by L1 and sin B by L2, we are going to solve for B, that is sin inverse L2 times sin A whole divided by L1. The values of A will be in range 0 to 180, and we need to generate a plot that will plot the distance traveled by piston as a function of this angle A. Step 2 is specifying the inputs that is to be used by our program. Here we clearly know the input is the length of connecting rod L1, length of crankshaft L2, and the angle A between crankshaft and the rotation axis, that is angle A. Step 3 is specifying the output to be used by our program. The output we want from our program is plot of distance traveled by piston, that is D, versus the angle A. Step 4 is working the solution of each step by hand or by calculator. We know that the triangle collapses at A at 0 degree and at A at 180 degree. So we will definitely check our values at that time, and we get the distance as L1 and L2, L1 plus L2 at A equal to 0 and L1 minus L2 at A equal to 180 degree. Similarly, for other angles, we get values as populated in the table. So at 0 degrees of A, we get value of 1.5, that is nothing but L1 plus L2. At 60 degrees, we get 1.15. At 90 degrees, we get 0.87. At 120 degrees, we get 0.65. At 180 degrees, we get 0.5. Step 5 is writing the program. The program for this is fairly simple. We define the length L1 and L2 as 1 and 0.5 respectively. We calculate the ratio of L2 by L1. We define a range of A from 0 to 180 and calculate the ratio for the same. We find the value of B with sine inverse of L2 times sine A whole divided by L1. We calculate the distance traveled by the piston D as L1 cos B plus L2 cos A, and we plot the same. The plot is shown with maximum at A equal to 0, that is 1.5 feet, and minimum at A equal to 180 degree, that is at 0.5 feet. Step 6 is to check the program with our calculated hand solution. As we already have the table for comparison, we can make out through the plot that at 0 we have 1.5, at 180 we have 0.5, and at 120 we have 0.65. So our hand calculated values do match with the plot. Step 7 is to perform a reality check on the output. So what are the possible reality check on the output for this problem? As plot is smooth and there is no abrupt changes and discontinuities, we can say that the plot behavior is expected. However, the plot shows D behaves as expected and decreases smoothly from its maximum at A equal to 0 to its minimum at A equal to 180 degree. So we can say that our program and output has passed our reality check. Step 8 is testing the program against a range of reasonable values. This is an optional step. We can further test the program for various values of L1 and L2 and various cases of values like values for L1 less than L2 or L1 greater than L2, something like that. We can examine these resulting plots and see whether the output still remains reasonable. This concludes our introduction to the Matlab IDE. This is just an overview of all the important features that are there in Matlab, problem methodologies, solution methodologies, and way we use the Matlab IDE to solve a particular problem. In the future videos, we will look deeper into the specifics of Matlab program, Matlab functions, and other relevant stuffs. So until then, please stay tuned.